it's time to start the lecture of John Chalker, classics as a quantum house.
Okay, thank you, and good afternoon, everyone. I'm sorry, I've got the wrong set of transparencies up there. Okay, I think that's the right set of slides. So I want to continue the overall program that I talked about yesterday. So yesterday I started out by trying to explain the general context for thinking about many-body chaotic systems and how this relates to a historical sequence of people thinking about chaos in the context of nuclear physics, and then in the context of low-dimensional quantum systems whose classical counterparts are chaotic, and then in the context of mesoscopics, and nowadays concentrating on many-body systems. And I talked about how in that area random matrix theory gives us a very good guide to the properties that we can expect for the spectrum. And in particular, if we have a chaotic system, then we believe that this leaves its fingerprint in the spectrum, provided we look at the spectrum within an energy range that goes out to some maximum. And that maximum, in the case of random matrix theory, would be set by the bandwidth of the random matrix, where the details of the random matrix model that we choose to study would have their effect. And in mesoscopic systems, it goes out to an energy scale related to the Thouless time, which I'll mention in due course, but set by system size. And then in tomorrow's lecture, I'll be arguing that there's a similar kind of energy scale in many body systems with local interactions. But in any case, the picture is that random matrix theory works well, provided we limit our attention to an energy window which may be wide enough to contain a very large number of levels, but has some upper bound. Or correspondingly in the time domain, we can think about timescales above some lower bound. So then if we switch our attention from energy levels to eigenfunctions and physical quantities that we might construct from the eigenfunctions, the point is that random matrix theory in itself can't really give us very much of a guide, because we constructed the random matrix ensembles with the idea that the choice of basis should be unimportant. We selected the probability distribution for the random matrix ensembles to be functions of traces of powers of the matrix, so that we had ensembles that are explicitly invariant under rotations, and so the set of eigenvectors across the ensemble is isotropically distributed. And then we come to the question, what do we expect if we go to some more realistic model for a physical problem? And at that point, I realize it's useful to say a few words to explain the things that are in common between the problems that I'm talking about and the one that we heard about from Alexei Kitaev this morning, the SYK model, to talk about the things that are in common and the things that are different. So clearly, with the Gaussian random matrix ensembles that I described, one feature is that with probability 1, all of the matrix elements in some fixed basis are non-zero. Now, if you think of some more physical model, if we go to nuclear physics as the original motivation, and you think of some physical set of basis states with particles in different orbitals and so on, then most matrix elements of the many-body Hamiltonian are going to be zero. And if your Hamiltonian only contains few body operators, the only non-zero matrix elements will be ones between states in which just a few particles have shifted. And clearly, that was a feature of the SYK model that we heard about this morning. So if you want to go to a more realistic model of a physical system, then for sure, one thing that you should do is go from having a random matrix whose entries are all non-zero to having something more structured with at least the non-zero matrix elements limited to some choice of few body interactions, such as in the SYK model with Q of the Majorana fermions coupled together by each term in the Hamiltonian. But there's another direction that you might like to go in additionally, and that's to have a spatially extended system. And it's that aspect which was clearly there in the quantum circuits that we also heard about this morning in the lecture from Tomasz Prozan, and it's that aspect that I'll be emphasizing myself. And the difference between something like the SYK model and quantum circuits is quite significant when you come to probe properties. And the basic point is that in the SYK model, you kind of automatically have a high-dimensional Hilbert space by taking the thermodynamic limit, but with no spatial structure. Whereas in quantum circuits, in general, if you have a local Hilbert space dimension, the limit of large Hilbert space dimension comes with the limit of large spatial extent. Okay, so coming back to this plan, when we talk about generic properties of chaotic quantum systems and go from the spectrum to properties of eigenstates, then one way in which people have tried to characterize eigenstates is via what I started talking about last time, what's known as the eigenstate thermalization hypothesis. And then with something like a quantum spin chain in mind, the point is that for a system like this, we can't simply think of the eigenstates as superpositions of random waves with some constraints on the sum of the wave vectors to say that the state has a certain energy. And instead, the picture is more like this. If we go between two similar systems, then the eigenstates in the second system we can think of as random superpositions of eigenstates from the first system. And that sort of idea is what leads you to the eigenstate thermalization hypothesis, But it's easier to write down what a hypothesis is than it is to give a formal derivation. So I'll run through quickly the statement of the hypothesis, and then the final point that I wanted to make in connection with ETH, as it's called, is not a derivation, but at least an argument which is reasonably clear-cut, which I think helps to reassure you that it's a reasonable supposition to make. Okay, so to remind you of the hypothesis, we're thinking of some local observable in the system. We're not trying to characterize eigenstates globally, we're just trying to talk about their properties as far as matrix elements of a local observable are concerned, matrix elements between pairs of eigenstates of the Hamiltonian. And the statement is that there's a contribution to this matrix element which varies smoothly with the average energy of the pair of states, and that sits on the diagonal. And then there are some other contributions which fluctuate randomly, but they're small by this prefactor, and this prefactor is basically the size of the part of the Hilbert space that's relevant to the states that we're thinking about. And those fluctuations are modulated by some smooth envelope function, and then the individual randomness of the matrix elements is represented by this random matrix R, which is scaled so that its variance is 1, and in other respects it's a random matrix, and emission if this observable is emission. And then the point was that if we think of some generic state, which is a superposition of eigenstates, then for statistical mechanics to work, what we'd like is the average of the operator to be fixed by the expectation value of the Hamiltonian in this state. And we could build different states with the same expectation value for the Hamiltonian by choosing different values for these expansion coefficients. And that would be unfortunate if it made the expectation value of the operator fluctuate. And what stops that happening is that these fluctuating contributions to matrix elements are small, and the main contribution is smooth in energy. And then the other aspect of the hypothesis, which I won't talk about much, is that this envelope function really encodes the behavior of autocorrelation functions. Okay, well, as I said, I'm not going to attempt a derivation because there isn't some clean closed-form derivation. There are more plausibility arguments, but there is a consistency check which one can do, which I think is quite nice. So the point is, given this hypothesis for the matrix elements, what one can ask is, what does this imply for a matrix element of some different operator? And I could have chosen the product of two operators A and B, but the simplest choice that I might take is that this different operator is in fact just the square of the operator I was looking at originally. So we can simply take this hypothesis and work out implications for matrix elements in the square. And of course, the point is that we can take the matrix element of the square and insert a complete set of eigenstates, and then for the pairs of matrix elements that appear here, we can substitute from the original form for the eigenstate feminization hypothesis. So what we have is basically something like the square of the right-hand side of this top line. And when we make that substitution, of course, we get, well, 4 terms. One is basically the square of this term, which looks like that, and another is 2 terms that are cross products, cross terms between the first contribution and the second term contribution, and they look like this lower line, and then something which is basically the square of this second term. And the question is, does the right-hand side of this expression have the same form as the as we should expect according to the eigenstate thermalization hypothesis? And it's a basic minimum requirement that it should do, because if it didn't, then the whole thing would fall flat on its face. So we can compare the terms on the right here with terms in the original expression, and this first one, it's a Kronecker delta on the 2 eigenstate labels times something which is smooth in energy. So it's just a version of this kind of term, which we get by substituting A as B squared for AB. And in the same way, the last term here is of the same form as the second term on the right-hand side, because it's small according to this factor 1 over root n, and it's got this random matrix form, and we can match this up with that just by saying that twice A times F is a kind of renormalized version of the F that we had for the original operator that we were considering. So the real issue is whether this term that I skipped over is something which fits into the original pattern. And if we want to examine that, then it turns out that it's best to look separately at the cases of a diagonal matrix element when m is equal to n, and an off-diagonal matrix element. So if we look at the diagonal matrix element, then this term, if m is equal to n, then what we've got is the modulus squared of Rmp, and that's something which on average is 1, according to our assumptions about these random matrices, with fluctuations. So if we think of the sum here, we're summing the square of this is something positive, and the number of terms in the sum, well, this curly n is effectively the number of states in the Hilbert space that contribute to these sums, given these envelope functions. So what this sum is essentially is a sum over n terms, which are all positive, and then thinking of the law of large numbers and taking into account this 1 over n prefactor, what that gives us is an average which is something of order 1, and fluctuations which are 1 over root n. So this average we can combine with the first term to say it's part of the smooth part of the ETH, and these fluctuations we can combine with this fluctuating term. And the point is that we've got a result that fits into the same form as the original formulation of ETH. And if we look at the off-diagonal terms, then now this product of 2r's, since the indices are different, sometimes it will be positive, sometimes it will be negative, with an average of 0. And again, from the law of large numbers, if we sum over of order n random terms and take into account the prefactor, then we have a result which is random and of order 1 over root n. And so again, we get a contribution which is like the second part of ETH. So in other words, the idea of ETH is at least self-consistent, because if we assume one operator has matrix elements in form, then the same thing applies to other operators that we can form from the initial choice. Yeah.
So how do you reconcile this with the fact that, like, suppose A is poly matrix and you square it, it's identity matrix, and then
Sure. Yeah. Okay. Good question. So those properties involve matrix elements from some wide window, and I guess ETH only applies within some narrow energy window. So you have to restrict yourself to that narrow energy window before that. Yeah.
Could we see that the numbers that will contribute to some of the D is order of n? We just identify n with the kind of size of the relevant Hilbert space. That's how the argument goes. Right?
Yeah. So the idea is that the aim is basically the entropy of the system, is the exponential of the entropy of the system at the energy density that we're considering. Then for dimensional reasons, you should multiply that by some choice of energy window. But once you've taken the exponential, then that choice is, relatively speaking, unimportant.
So I'm just saying that the argument simply goes that whatever sum I have over states, unless certain constellations happen, it's typically O of n.
Yes.
Point. Okay. I see. Okay. So there's no more involved arguments, right? Just
That's right. Yeah.
Okay, thank you.
And then the final point that I wanted to make in connection with ETH is that when you look numerically, then you can see exactly the behavior that's claimed. So what I've got on this slide is just to do with the diagonal matrix elements of some operator. What's been done here is to diagonalize the Hamiltonian for a system that you expect to be ergodic, and then work out the diagonal matrix elements of some operator and order the states as a function of energy. And what this illustrates is that the diagonal matrix elements for all states at a given energy have only small fluctuations, and those diagonal values vary smoothly as a function of energy. And that contrasts with what happens if you look at an integrable system, where in some given narrow energy window you find eigenstates lying in that window, which have all sorts of values for the matrix element.
What is an ergodic system?
Sorry, what is? Yeah, okay, I think if I rewrote this slide, I might not write ergodic, because I guess you might point out that that's an idea which is clearly defined and so on in the context of classical mechanics. So what I'd simply like to say here is that it's a system that doesn't have any obvious conserved quantities beyond, I think in this case, particle number and energy. And if you looked at the spectrum of the Hamiltonian, then one measure that you could use as to whether the quantum system was in some sense chaotic or not would be whether the spectral correlations follow random matrix theory, and this example is. So it's some kind of hardcore post gas chosen not to be integrated. Okay, so now I want to move on to new points, which are basically to do with how we can characterize long-time dynamics in many body systems with local interactions. And the overall plan is to talk today about the quantities that you'd like to study, and then at the end of today's lecture about how you can set up random circuit models. And in the lecture tomorrow, I'll talk about how to actually do calculations of these quantities. So the issue really is what dynamics is there beyond the dynamics that you might have for conserved densities, which quite likely you can describe on the basis of, for instance, propagation of sound waves or diffusion of densities that you might have in a classical system. And pictorially, if you disturb a system, say at a particular point x, at time 0, how does that disturbance spread out? And the particular probes that I'll be talking about are firstly the dynamics of entanglement, and secondly spreading of operators. So when I talk about operator spreading, there's certainly going to be a fair amount of overlap with things that Alexei Kitaev has said, and I hope that, well, on the one hand, it should be useful because whereas he was talking about operator spreading in a system like the SYK model with no spatial locality, my emphasis will be on the consequences of spatial locality. And then secondly, hopefully the mental effort of your making a translation between his notation and mine will help fix the ideas firmly in your minds. Okay, so in general, we'd like to think about dynamics in a quantum system, and if we try to get some guidance from things that are familiar in single particle problems, then we might imagine one of the mesoscopic systems that I mentioned in my introduction. So, for example, some quantum device with random potential representing scattering of electrons by disorder. And we could, for instance, set the system up in a wave packet that's localized near a particular point and ask how that wave packet evolves. Well, most likely the probability density on timescales longer than the elastic scattering time would follow a diffusion equation, and if we have a finite system size L, then the density will relax to something roughly uniform across the system on a timescale given by the system size squared divided by the diffusion constant. And it's actually this timescale that was originally called the Thouless time in the context of disordered conductors. And so this would be a timescale beyond which random matrix theory would apply in this kind of system. So now we could ask whether there's some analog when we think about a many-body system and dynamics there. And in particular, we might do a rather similar kind of thought experiment where we prepare the system in some initial state in a computational basis and ask how it spreads in Fock space. And if the time evolution operator for the system has some conserved densities, and of course if it's a time-independent Hamiltonian, then at the very least we'll have energy density as a conserved quantity, and if we have local couplings, then there should certainly be a timescale for diffusive relaxation. But it's at least reasonable to think about systems that don't have any conserved densities, and in fact, the quantum circuits that we're talking about here are precisely examples of systems where, unless you choose to build in some symmetries, you don't expect any conserved density, because writing them in Hamiltonian notation, they'd be represented by time-dependent Hamiltonians, and because of the time dependence, you don't have energy as a conserved quantity. And so, under those circumstances, we expect much more rapid spreading of the wave packet in Fock space than if we did have conserved densities. And in fact, for the random circuit models that I'm going to talk about, it's easy to see that if we go from an initial state to a final state, which are both product states in the computational basis, and we look at the probability for that to happen, and we average over the ensemble of systems, then that becomes essentially uniform in one time step. So the question is that equilibrium? And one sense in which you see that it's not equilibrium is when you look at entanglement dynamics or when you look at operator dynamics. Yes?
So where does this relation come about between conserved quantities and time scales for realization?
So you mean, why is it reasonable to talk about this? Well, it's very elementary, and I don't think there's a more sophisticated version of the argument, but the elementary one is that if it's correct to think of the evolution of the conserved density, at least moderately long timescales as being described by a classical diffusion equation, then following the classical diffusion equation, if you start with a density that's concentrated in some small region of the system initially and ask how long it takes to relax, then this timescale is the answer. I mean, just from undergraduate calculations with the diffusion equation. And then if you ask, well, what's the justification for using this classical diffusion equation, then it probably depends in detail what specific system you have in mind. But for example, one system where this kind of behavior comes out from quantum mechanical calculations is a single particle model of a weakly disordered conductor. So you have a particle moving in the continuum with a Schrödinger equation with the usual kinetic energy and a potential energy which is a random function of position to represent impurities. And if the potential energy has small fluctuations, so that you're not in an absolute localized limit, then you can show in a controlled way that you get to a diffusion equation for the spreading of probability density.
But in the absence of conserved densities, so
Why why should things relax faster? Well, it's not completely obvious that they would. This result, it's a very simple calculation, but to explain it, I need to say something about random quantum circuits and averaging. So it's something which it would be easier to talk about at the end of tomorrow's lecture. Yeah.
Maybe I don't really get the notion of this uniformity in one time step. So at this point, you're basically saying that if I take a generic initial state, then the result will be uniformly distributed across the Hilbert space in terms of a final state, right?
Well, I'm not claiming by all measures that
Yeah,
it
but
will
I mean-
be, but the crudest measure that you could ask would be simply the probability of getting from some generic initial state to some generic final state, and then averaging that probability,
Yeah,
which matches what I was talking about there.
Yeah, because basically I was just making sure that it's not about just picking literally any state, because obviously I can just pick, let's say, all spins down for a network or for this kind of circuit that okay is random, but it's gonna flip only a handful of spins probably, or just if I just take this all spins down, flip just one spin and see how it leaves.
Well, yeah, I mean, it's reasonable to examine the claim. So let's think about something which is maybe the most unlikely sounding possibility, that I go from all spins down to all spins up. But then you need to remember that across the system in one time step, all of the gates act in parallel. So provided there's some chance for the gates to flip the spins.
I was just asking whether it's like more of a hand-waving statement than very legit.
It's not completely hand-waving, because this claim you can work out straightforwardly. For instance, if you have hard gates.
Okay.
Okay, so the point there is that it's worthwhile looking at quantities which will test equilibrium in a more sophisticated way, and two examples are to look at entanglement dynamics or operator dynamics as probes. And now I come to one of the difficulties that I had planning these lectures, of not knowing what kind of background people have. So it may be that some of what I'm going to say for the next few minutes is extremely familiar to you, but in case people hadn't thought much about density matrices, I thought I should at least remind them of some basics. So if we have a complete orthonormal basis, and we have the idea that the system has some probability to be in each of these possible states in the basis, then the density matrix represents that idea. So it's a matrix whose eigenvalues all lie between 0 and 1, and physically they give us the probability for the system to be in the corresponding state. So two simple examples of density matrices are firstly a pure quantum state, where I simply take a single state, the ket and the corresponding graph, and in this general expression it corresponds, of course, to taking one of the probabilities for a selected state to be unity, and the other probabilities therefore to be zeros. Or in a thermal state, the probabilities are all the corresponding Boltzmann probabilities for the different states, and in that case, the states should be energy eigenstates, whereas here I could write a pure density matrix for any state that I might be interested in. And then you can characterize this density matrix in various ways. Sorry, I also wanted to say as part of the basics that if we think about time evolution, then since this is formed from a ket on the left and a bra on the right, if we time evolve, we multiply by the time evolution operator from the left and its Hermitian conjugate from the right. And then one way to characterize density matrices is, well, essentially by the distribution of probabilities, the distribution of eigenvalues, and we can talk about those in the same way that we do in other areas of statistical mechanics. We can talk about entropies, and most obviously the von Neumann entropy, which is in the usual way trace of rho log rho. Now, that's fine, but when we come to doing calculations, then taking the logarithm of a density matrix is something which is difficult to do, and one has to use replica tricks of the type that Alexei Titayev mentioned this morning. But often you can get useful information without doing that, and there are versions of entropy which avoid that based on traces of powers of the density matrix. And if I wanted to define the Renyi entropy directly, I'd have to take a log of this trace, but here I've simply written the exponential of the Renyi entropy in terms of a trace of the power of the density matrix. And in the simplest case, I just take this power to be the second power, and that's also known as the purity. And these Renyi entropies enable us to get different things. And for instance, if I take the limit of this label alpha to 1, then that gives me the von Neumann entropy. And if you're coming across these things for the first time, it's useful to think about some special cases. So if I take a pure state, then the entropies are all 0, basically because one of these eigenvalues is 1 and the rest is 0, so either the contribution to rho vanishes or the contribution to log rho vanishes, and similarly for the Renyi entropies. And then in the other limit, if I take a maximum mixed state, the infinite temperature limit of the thermal state, then all of these probabilities are equal, and by normalization, they're one of the Hilbert space dimension. And in that case, you find that all of the entropies are log of the dimension of the Hilbert space, regardless of the value of alpha. So as you vary the distribution of density matrix eigenvalues, the entropies go between 0 and this maximum value. And then finally, often we'll be thinking about a system of lattice sites. So we have L lattice sites, and on each lattice site we have a local Hilbert space dimension Q. Then the Hilbert space dimension for the whole system is Q to the power L, and so this log n becomes n log Q, so the maximum entropy is log Q per site.
A question?
Yes.
Can you go back to maybe this is an annoying question, but
Yes.
I mean, so you said, okay, mixed density matrix is like with some probability you're in one state or the other. Do you really think of thermal state as like let's say it's a chaotic spin chain, whatever. Eigenstates are very complex, entangled, unphysical objects, like states of the system. So do you really think of thermal state as a system which is oscillating between these sort of unphysical state to some probability? I mean, it seems strange to me.
Well, all right, maybe the better way of thinking about that comes when we talk about reduced density matrices, which I'm sure you're familiar with, but which I'm going to review next. Okay, so this is the beginning of the point that I wanted to make. So, I mean, the basic question in this area is how unitary, sorry, this misprint there, how unitary dynamics can lead to equilibrium. And the point is that if we start with a density matrix for a pure state, then the effect of this time evolution is to rotate the state vectors, but it leaves the density matrix itself pure. And so if we calculate, for instance, entropies for the from the density matrix of the whole system, they can't change in time. And one way to resolve this central question is to say that, well, equilibration is something that only happens when we look at subsystems of an isolated system. So, for instance, suppose we have this system and we have a plan to make measurements on some part of the system, but we're not going to observe anything in the complementary part. So we can work out the results of measurements in part A without knowing the density matrix of the whole system. In fact, we can take a trace over the degrees of freedom in the other half of the system. And so we can think about the reduced density matrix. If you haven't thought much about reduced density matrices before, then I think it's important to play around with them, and I have a couple of rather simple examples. So the very simplest one you can construct is to think about a system consisting of two spinor halves, and we can compare a state which is unentangled with an entangled state. So a spin polarized state with a spin singlet state in this example, and the idea is to work out the reduced density matrix, and we do that by taking a trace over the degrees of freedom in the complementary part of the system, and completely explicitly that means that we sandwich the density matrix between either upspins in subsystem B or down spins in subsystem B, and the result will be a density matrix for the subsystem A, that's to say a single spin and a half. If we do that with the unentangled state, then the density matrix that we get is simply this pure state for the subsystem, and so it has, of course, entropy 0. But if we do it with the entangled state, then when you take this entangled state and its Hermitian conjugate to form a density matrix, then you'll get 4 terms from multiplying out the 2 terms in the ket and the corresponding 2 terms in the bra, and then we take the trace over states of subsystem B. So when we do that, if we take this ket with the corresponding bra, then this will give us a term which will be both spins in A up. And if we take this with the partner bra when we form the density matrix, and look at this contribution when we evaluate the trace of B, it'll give us a term like that. And then we'll also have some cross terms where we have, say, the ket here with bra in which the spins are the other way around, but those won't contribute when we take the trace over subsystem B. So this expression will be the final one for the density matrix, the reduced density matrix of our spin A, and this is a mixed state, and it would have von Neumann entropy of log 2. I thought it would be worthwhile talking about one other jolly problem, and that's to think about what happens when we have some arbitrary size Hilbert space, and we think of a randomly oriented vector in the Hilbert space, and we average, well, to keep things simple, I'll average the purity or the exponential of the second Renyi entropy. And so the motivation for an example like this is that you might think that even if we start a system off in a rather special initial state, for instance, with all of the spins up, then with some generic Hamiltonian, under time evolution, it will evolve into a vector that might almost as well be randomly oriented vector in Hilbert space. And so it's worthwhile knowing what the reduced density matrix would be like in that kind of situation. And the simplest way of characterizing that reduced density matrix is to work out the purity. So there's some notation. This randomly orientated state in Hilbert space are right as a ket psi. And then I'll think of some basis vectors, which are simply vectors in some computational basis. Say, if we're thinking about spin and a half, they'll have different orientations of the spins on each side. And so if we expand our randomly oriented vector in these basis states, then the expansion coefficients I can write u sub I, where I labels the basis states. And then in terms of these expansion coefficients, well, that means that a matrix element of the density matrix that I form from this vector will be u sub I times u star sub j from the overlaps between psi and I, and between the corresponding bra and the state j. Okay, but now I want to think about taking the trace over the states of one system, one subsystem, and so this label I for the basis vector, I should separate into a group of labels that tell me about the state of the first subsystem, and another group of labels that tell me about the state of the complementary system. And I've got equations on my slides, but I realized in Thomas Pleasant's talk this morning that it's actually much better to draw pictures, so let me draw some pictures. So what I'm saying is that I have something representing the ket psi, and I'm going to have some legs on it, one which will tell me about what's going on in subsystem B, and another that will tell me what's going on in subsystem A. And I'll have another symbol representing the corresponding bra, and I have labels like that. And I want to take a trace, so this combination represents the density matrix. And what I want to do now is work out the density matrix for the subsystem A by taking a trace over subsystem B. which I exclude that. And then I want to characterize some properties of this reduced density matrix, and in particular, my plan is to work out the purity, which is the trace of the square of this matrix. So if I want the square of this matrix, I better write down the same thing again. And for future convenience, I'm going to, when I write this down again, I'm going to rotate it by 180 degrees through an axis going through the board. So if I've done that correct, then this will be rotated to there, and this will be rotated to there. And this, I better have some arrows to indicate the way in which the matrix order is arranged. So that arrow indicates that there, and here I'll have a similar loop in B, and if I rotated this by 180 degrees, then this will be going up. And because this is arranged like that, there should be arrows here going out on the top and in the bottom. And here, after the rotation, this is an inward going arrow, and here's an outward going arrow. And so now I multiply these together and take the trace, and what I have is a picture like that, which is represented in this way. I have 4 of these amplitudes because I've got 2 powers of the density matrix, and then I have some combination of Kronecker deltas, which are represented by the lines on the board. Okay, and then as the core step in this calculation, what I should do is average over all orientations of this state vector, which means averaging over these amplitudes, and in particular, averaging over this product of 4 amplitudes. And, well, I've stated the result here, but let me say a little bit to try and make it plausible. So what we've got is amplitudes ui, u star j, uk, u star l. And remember, these are amplitudes of a vector in some high-dimensional Hilbert space, and now we want to average over all possible orientations. And part of that averaging could be averaging over faces of each of the components. And when we do an average of that kind, the result will vanish unless we pair the labels together on the u's and the u stars. So one way of pairing the labels, of course, would be to pair them like that. And the alternative way of pairing the labels would be like that and like that. And if we do pair the labels in one of those 2 ways, then we get a non-zero average. And since these amplitudes in an n-dimensional space, we expect each of them by normalization of the wave vector to be of order 1 over root n. And so when we've got 4 of them together, we get something which is of order 1 over n squared. And the full result is written here. So the 2 sets of Dove functions correspond to the 2 ways of averaging that I've drawn in blue, and this idea that it's of order 1 over n squared. Well, the exact result is slightly different, but not very different. So if you follow the details, then the next step is to simply do all these sums, taking account of these Kronecker deltas. And when you do that, what you find is an exact expression like this. And then really to understand it, it's worth simplifying. And a natural thing to say is that the part of the system where we're not going to make any observations is much bigger than the part that we are going to use for our observations. That's to say, the Hilbert space size for B is much bigger than the Hilbert space size for A. And in that case, we only want the first of these two terms in the numerator. And then the other thing that we should remember is that the Hilbert space size for the whole system is the product of the Hilbert space sizes NA and NB for the subsystem and its complement. So we can cancel NA and B with the n on the bottom, and then if n is large, n plus 1 and n similar, so we have a remaining factor of nb over n, which is 1 over na. So what does that tell us? Well, if all of the eigenvalues of the reduced density matrix are of the same size, then by normalization, by the fact that the trace of the density matrix is 1, those eigenvalues should each be 1 over the Hilbert space dimension, that's to say 1 over A, and so if you square them and then take the trace, the result would be 1 over NA. So it's consistent with this reduced density matrix being maximally mixed, and there are much more sophisticated calculations that you can do which show that in fact the fluctuations are small and all of the eigenvalues are 1 over NA in the limit that I'm talking about. Okay, so that was trying to give some illustrations of how things work with reduced density matrices, but now we want to go back to thinking about time evolution. And at this stage, I just want a rough picture, and in the lecture tomorrow, I'll talk about specific calculations. But the rough picture that we begin to develop is like this. So, I mean, for instance, suppose you are considering a spin chain and you start the system off at time 0 in some product state, and then you think about the consequences of time evolution. Well, time evolution might set up some singlet pairs in the wave function, and when we look at the reduced density matrix for a subsystem, the consequence of these singlet pairs, which span the division between the two subsystems, will be that the reduced density matrix for the subsystem is not the one for a pure system. It's a mixed density matrix, as in the example of 2 spinor halves. So what you expect is that if you start with some low entanglement initial state, then, well, if statistical mechanics is justified, then at long times, you should wind up in a thermal state with some temperature fixed, if we're thinking about Hamiltonian evolution, by the initial density. If we have local interactions, and if the subsystem we're looking at is spatially extended, then you can imagine it'll take a long time for this equilibration to happen. And so if we work out a reduced density matrix for a subsystem as a function of time, we can imagine there would be some sort of picture like this for its time dependence. What you'd like to know is the shape of this curve and the time scale for saturation. One of the attractions of random quantum circuits is that you can do those calculations explicitly. Okay, so one of the ways in which we can probe dynamics is by looking at entanglement growth, and the other way is by thinking about operator growth, about the dynamics of observables. So one point is that the discussion of equilibration there was based on the idea that we might start the system in some initial state which was very different from a thermal state, for instance, a state with low entanglement. But if we think about the dynamics of observables in the Heisenberg picture, then we have a direction we can think about that doesn't refer to quantum states at all. And so to repeat in my notations and things that I think you've heard from Alexei Kitaev, we could think about an initial observable, which is perhaps in a spin chain, one component of spin acting on a particular site, and if we write the operator in full detail, then we want to say that there are identity operators acting on all of the other sites of the system. And what you expect is that under time evolution, this simple initial operator will evolve into something which you could call a sum over strings of operators acting at many sites, and different terms in that sum will involve operators acting, say, on a sequence of sites in the middle of the system, but then acting as the identity outside that set of sites. And so you have an idea of a support of the time-evolved operator as being the set of sites where it acts non-trivially. So if you want to describe this formally, then one language to use is to say that you think of operators as vectors, and one way of formulating that is by going to double vectors, but let me explain things in a slightly different way. And the point is basically that operators are, in the usual sense, elements of a vector space, and to define a vector space, of course, what we need, one of the ingredients that we need is a definition of a scalar product, and a convenient scalar product to use is a trace of the product of two Hermitian operators, normalized, and the normalization I'm using is the dimension of the vector space. So if we have a set of operators, we can set up an orthonormal basis, choosing the operators to be normalized to unity, and choosing different operators in the basis to be orthogonal to each other in the sense of this trace. So if you think of a single spin and a half, then of course an orthonormal basis of operators is represented by the Pauli matrices, and they have just these properties. So that gives us the language to think about time evolution of an operator, and then the statement that the operator evolves into a superposition of strings is to say that we take, not just for a single site, but for the system as a whole, our basis operators to be sequences like this, and if we're thinking of spin and a half, then they'd be sequences of unit operator acting on some sites and some of the Paulis acting on other sites, normalized in this way. And then as time goes by, we can talk about the evolution of the operator in the Heisenberg picture in terms of evolutions of these amplitudes for the different operators in the basis to contribute. And that's a very useful language for discussing time evolution, and it's particularly useful because there's an exact parallel with the evolution of wave functions, and the point is that the probability which you can construct from these amplitudes is conserved as a function of time. And you can check that perfectly straightforwardly by substituting these definitions into the Heisenberg equation for the time inclusion of the Okay, so now we have some parallels with what you were hearing from Alexei Kutaev, but also some differences. So what we're interested in is how the contributions to this sum evolve in time, and in something like the SYK model, the number of significant non-zero terms increases as time goes by, and that's also true in systems with a spatial structure like the quantum circuits that I'm talking about. But there are differences as well in the way that happens, and in particular in systems with spatial structure, we can be interested in the size of the support of the operators that contribute to the sum, and how the size of that support changes in time. And the basic fact is that this support size grows in time, and one way that you can probe it is by looking at the commutator between the time-evolved operator, which started off from something that was local at a point, a site Y in the system. You look at its commutator with a local operator at some point X in the system. And a long time ago, 1972, before any of this work on many-body quantum dynamics really took off, Elliott Leeds and Robinson appreciated that this was a fundamental question to ask, this question about the growth of the support, and they proved a very important and rigorous theorem on this. So the basic idea is that if X and Y are widely separated, and the support of Y as it's evolved to some time t is small, that's to say not small enough to overlap with the site X, then these two operators will commute with each other. And so by looking at the value of this commutator, we probe the spreading of the operator. And what they proved is that the commutator is small if the two sites X and Y, well, if the site X is, I've got the labels the wrong way around, it should be if the operator O of X is outside this light cone. So we have a picture like this with one operator spreading in time, and if the other operator is outside this light cone, then the commutator is small. And the velocity at which this light cone grows is, of course, set by the couplings in Hamiltonian. So, as I said, this is a rigorous theorem, and I'm not going to attempt to go through the rigorous proof, but you can actually get an idea rather easily of why it's reasonable in the following way. So we need to think about time evolution, and so we're thinking about exponentials. And if you think about the power series expansion for the exponential, which after all has an infinite radius of convergence, then for a given size of this argument x, the terms decay rapidly if you go to a high enough order. In fact, if you go to an order beyond what I've called n max here, which is set by the magnitude of x. And if you apply that idea to the time evolution operator, then you can leave out terms in the power series expansion beyond some maximum order, and that maximum order would be set by, well, it would be the time variable t times the operator norm of the Hamiltonian. So if you leave out the terms in the expansion of the exponential beyond this cutoff, then in what's left, you've only got the Hamiltonian raised to a finite power. And if the Hamiltonian is a sum of local terms, then raising it to a power gives it, from products of those local terms, a range in space which grows linearly in n. And then the cutoff will increase linearly in t, and so this range increases. And if the operator x is outside the range of the time-evolved operator y, then the commutator is small. So then I thought I should link this idea of operator spreading to the OTOP, which I realize you've heard about from Alexei. The point is that one way of probing the commutator is to look at an average of its modulus squared, and take modulus squared because if we're going to do averages, then the commutator itself might average to 0 without being 0 in every state, simply because of fluctuating signs. And we expect this commutator to be small if we're outside the light cone and non-zero if one operator is inside the light cone of the other. And then to talk about details, it's convenient to take the density matrix, which you might put into a thermal trace, thermal average, simply to be the infinite temperature density matrix, and to think about operators which are like Pauli operators in that they have a trace of 0 and they square to unity. And then if we look at this trace, or in fact for convenience multiply it by half, if we expand the square of the commutator, then the commutator has two terms. We get four terms, which are two different types. One of them, which comes with a plus sign, involves the trace of squares of operators, and the other involves the operators in this out-of-time order sequence, so going from y at time 0 to x at time t, and then back to y at time 0 and forward to x at time t, we can simplify the first term if the operator is square to the identity, and we've got this 1 over n normalization, then the first term is just unity, and the second term contains the information we're interested in, and that's what I'll be thinking of as the out-of-time order correlator. And the behavior that it has is that it's, well, with these normalizations, it's unity at short times, and then it falls to 0 when the operators enter each other's light cones. So the idea is that at short times, if the points x and y are well separated, these operators commute with each other, so I can change the order and change it to O of y squared and O of x squared, and those are both unity, and so this correlator is 1 at short times, but at long times, the time evolution essentially means I'm looking at something like infinite temperature average of each of these operators, and since the operators independently have trace 0, this correlator falls to 0 at long times. Okay, so the picture is that those give us two ways of characterizing dynamics in in a many-body quantum system. And now we'd like some simple models which will be quantum circuits. And if you start off with the question, how can you construct convenient, and by convenient I guess I mean solvable, models of many-body chaotic systems, then one lesson from random matrix theory is that in general, individual non-integral models won't be likely to be solvable, but something that you can hope to do is calculate properties averaged over an ensemble of systems. And so what we'd like to do is combine random matrices so as to make our ensembles, but to build in some spatial structure, which of course is what was missing in random matrix theory as it was originally formulated. And then there's one further point which I think is a guiding principle, and that is that in the probes that I've been talking about, both of entanglement dynamics and of operator dynamics, it was really time evolution that played the central part, and so it makes sense to try to model the time evolution operator directly, rather than, first of all, thinking of a convenient model Hamiltonian, and going afterwards to the time evolution operator. And it's these two principles that take us to the idea of quantum circuits. And to represent a quantum circuit, we need just the kind of picture that we saw this morning in Thomas Preser's lecture. So this is a space-time diagram with space going horizontally and time vertically, and it's really just for convenience drawing the picture. The space is one-dimensional, and things don't get much harder in higher dimensions. And the idea is we have a lattice, and at each side of this lattice we have a local Hilbert space dimension, local Hilbert space, whose dimension I'll call Q. So in the simplest example, this would be spin half. And at least in the picture I've drawn, the time evolution proceeds by acting on these spins or generalized spins with unitary operators, which are called quantum gates. So here we act on the first and second pair of spins, the third and fourth, and the fifth and sixth, and so on. And then in a subsequent time step, to ensure the whole system is coupled together, eventually we can act across differently chosen pairs of spins. So when we think of the details of how we might do this, well, in order to make the calculations tractable, we'll pick the gates from the Haar distribution. So we'll take these unitary matrices representing the individual gates to be uniformly distributed over the unitary group. And we'll calculate ensemble average properties. But we still have some choices. So one is to choose the size of the local Hilbert space dimension. Another is the details of the architecture of the circuit, whether we use that brick wall structure or something different. And the third, which I'll mention, is to talk about symmetries. Yes?
How important is it that we always only act on neighboring sides?
No, it's absolutely unimportant. I mean, there are various things that you could do. You could act on second neighbors or third neighbors, or you could go in the direction of the SYK model and at each time step pick out completely at random a pair of spins with no attention to how far apart they are on the lattice, and then act on that pair of spins with a gate. And of course, if you make a choice like that, you wouldn't have local structure in space, but you might still have interesting dynamics. So then in practical terms, when you do calculations, you're going to need to average over multiple copies of the gates. And these averages are something that you can do for general Hilbert space, local Hilbert space dimension, if you only have a few copies of the gate. And it's something that you can do at all orders in the number of copies if you're willing to take the limit of large local Hilbert space dimension. So when you try and implement those ideas in more detail, then one choice that you have is when you consider an evolution operator which, well, in Hamiltonian language, is random in time. And what I mean in terms of this picture of gates, that each time a gate appears, it's chosen independently from, for instance, the hard distribution. And, of course, choosing the gates independently means that we don't repeat a given unitary matrix representing one of these gates many times, and so you can do exact calculations with general local Hilbert space dimension. But the other thing that you might be interested in doing is constructing a Floquet quantum circuit. And so Floquet, meaning that in a Hamiltonian formulation, the Hamiltonian is time dependent, but periodically so as a function of time. And then in these pictures, what that means is that the gate that acts on the first and second spins, each time it acts, it's the same gate selected once from the random ensemble, and the fact that I've got the green color repeated is meant to signify that it's the same gate, but the gate acting between the second and third spins is chosen independently of the one acting between the first and second spins. So I've used a blue color for this gate whenever it appears, and so on and so forth. And there are other things that you can do. It turns out that if you take the local Hilbert space dimension to be large and you use these brickwork models, then the coupling between sites is rather strong. And so it's sometimes convenient to have models where you can have tunable coupling strength between the sites, but still the convenience of hard distributed unitaries in the definition of the model. And one way of doing that is with something like this, where you use two layers with the lower layer introducing randomness in a convenient way, and the upper layer introducing coupling between the sites, again in a convenient way. So more explicitly, we can take this lower layer to be a product of independent unitaries on each site, and the upper layer we can take to be some diagonal unitary in a computational basis with phases that depend on the states of pairs of neighboring sites. And then, for instance, you can take these phases to be Gaussian random variables, and if they were all zero, then there would be no coupling between different sites. So the coupling strength is given, for instance, by the variance of these spaces. But in a way, the message that I want to finish with here is that there's a lot of flexibility, and if you have a problem of your own that you'd like to study, then there's lots of scope for designing circuits that would be suitable. For example, I emphasized that in these Floquet systems with a circuit that's random in time, we don't have energy as a conserved quantity, but one thing that has been useful to do is to reintroduce a conserved density, so you can make a local Hilbert space dimension, which is a local Hilbert space, which is the direct product of the original Hilbert space with an extra degree of freedom, that's say a spin half. And then you can make sure that there's U1 symmetry associated with the spin half, so that the Z component of spin is conserved by these gates. And the way to do that is to take the two-side gate to have a block structure where I am noting down the up and down labels on the two sides, but I'm not drawing in the labels for the states in the other part of the Hilbert space. So this matrix is, well, the Hilbert space dimension is 2q on each side, so a matrix that's acting on a pair of sides has dimension 2q times 2q, so 4q squared. But if we want to conserve Z component of spin, then we should give it a block structure like this, and we can choose independent half unitaries in each of these blocks to give us the kind of possibility of exact calculations in the circuit. Okay, so I'll finish there. In this lecture, I said something about the eigenstate generalization hypothesis, which tells us about the statistical properties of matrix elements of observables, but doesn't really give us any insight into long-time dynamics. And to talk about long-time dynamics, as I discussed, we can think about entanglement entropy of subsystems and how that evolves with time. And we can also think about operator dynamics and the behavior of the OTOP. And then finally, I talked about how you can construct random quantum circuits as models in which you can have true calculations. And in the lecture tomorrow, I'll try and give an outline of how those calculations